Hello everyone, my name's Iman. Welcome back to my YouTube channel. Over the past 2 years, I've loved creating educational content for you, and I'm always so grateful for your love and support, as well as your feedback and suggestions. My goal will always be to provide high quality, accessible resources for everyone, free of charge, no subscriptions required. Now, I'm currently working on refreshing some playlists to improve things like audio quality, address content gaps, and just keep the content updated. My focus is on being as thorough as possible, taking into consideration different backgrounds and learning needs. And I'm so excited to continue this journey with you. I've just redone my entire general chemistry playlist, and this physics and math playlist is next on my agenda. For each video, I'm going to have a link in the description box below where you can download the notes and the transcript. You can actually download the notes for each chapter, or you can download the compiled notes PDF. Regardless, I would recommend downloading the blank notes and trying to fill them in with me. We're going to be study buddies, and I'm going to help you work through everything. So let's go ahead and get started. Today, we're going to begin with Chapter 1, titled Kinematics and Dynamics. In this chapter, we're going to cover several key objectives. The first objective is titled Units. So we're going to start by discussing the units of measurement, focusing on the distinction between base and derived units. We're also going to cover important metric prefixes that are commonly used, and we're going to cover dimensional analysis. The second objective is titled Vectors and Scalars. So we're going to explore the differences between vectors and scalars, and then we're going to learn how to add and subtract vectors, how to multiply vectors by scalars, and how to multiply vectors by other vectors. Now for the latter, we're going to introduce the right-hand rule. The third objective is titled Displacement and Velocity. So here we're going to differentiate between distance and displacement, and then speed and velocity. Additionally, we're going to cover acceleration and how it fits into these concepts. Our fourth objective is titled Forces and Friction. So here we're going to start by distinguishing between contact and non-contact forces. Then we're going to explore key types of forces such as gravity and friction. Then we'll also compare mass and weight and discuss the concept of center of mass. The fifth objective is going to be on Newton's laws. We're going to define each law and provide examples to illustrate them. This is going to set the foundation for our next topic, which is motion with constant acceleration. Here we're going to explore linear motion, free fall motion, and projectile motion. We'll also cover motion on inclined planes and circular motion. Then our last and final objective is going to be titled Mechanical Equilibrium. So here we're going to have a discussion on mechanical equilibrium as well as free body diagrams. So that's going to be all of the objectives we're going to cover in this chapter. It's a lot, but we're going to take it one topic at a time. Our first objective is units. Before we dive into a discussion on motion, it's crucial to establish a consistent vocabulary that we're going to use throughout this course. Physics, it relies heavily on the language of mathematics to describe and explain the world around us. However, these mathematical expressions would be meaningless without units. Why is that? Well, physics involves experimentation and measurement. To communicate these measurements accurately, it's essential to use appropriate units. Every measurement must be expressed in units that clearly convey what's being measured. Now, the agreed upon unit system among scientists is the SI system, which is based on the metric system. There are 7 base units in the SI system, and I have them listed in this table here. For mass, we use kilogram, meters for length, second for time, Kelvin for temperature, ampere for electric current, mole for amount of substance, and candela for luminous intensity. These units, they're standardized and they're universally accepted, and they form the foundation for all measurements we're going to discuss. All other units you might be thinking about or are familiar with are just derived units, which are obtained by combining the SI base units. So again, we can use SI units to obtain derived quantities, and derived units are created by combining base units. A key example is volume, which measures the amount of space an object occupies. Volume is expressed in cubic meters in the SI system. Now, you can calculate volume for a cube, for example, using the formula that volume is equal to length times width times height. Since all three of these dimensions are measured in meters, multiplying them gives us a unit of cubic meters, which is a derived unit. Now, units are frequently modified through the use of metric prefixes. You can add these prefixes to make it more reasonable to refer to different values of length, mass, or time, depending on the system you're referring to. So, for example, if you're referring to a human cell, you don't want to say that a human cell is anywhere between 0.00001 and 0.0001 meters, when instead you can say that a human cell is anywhere between 10 to 100 micrometers. So in short, units are modified using metric prefixes to make it easier to refer to different magnitudes of a quantity. And these prefixes allow us to express very large or very small values more conveniently. So what you see here is a useful table of metric prefixes and their corresponding powers of 10. And they range from something very large like giga, which is 10 to the power 9, to something very small like nano, which is 10 to the power minus 9. These prefixes are essential for simplifying the expression of measurements in physics. Now, it's very important that you familiarize yourself with metric prefixes for the MCAT. With this discussion on units of measurement, it's also important to understand how to use them effectively in problem solving. This is where dimensional analysis comes in, which will take what we just learned about units and demonstrate how we can interconvert between them. Dimensional analysis provides a straightforward way to interchange units, and it's extremely useful in science. By following a set of simple steps, we can use dimensional analysis to solve problems involving measurements expressed in different units. So let's start with this. Every measurement has two parts, a number and a unit, neither of which has meaning without the other. But a given measurement can be expressed using different units, and so it's often necessary to convert a given result from one system of units to another. And that means conversion factors are going to be used to cancel unwanted units and obtain your final answer in the desired units. Now, what you see here are some common conversion factors that I would recommend you familiarize yourself with, and that are going to make carrying out dimensional analysis a lot easier. So how exactly are we going to tackle converting units? We're going to follow 3 simple steps every time we tackle a dimensional analysis problem. Step number 1 is to write down what you want to know. Step 2 is to start with the given measured quantity. And step 3 is to apply conversion factors in order to cancel unwanted units. So let's go ahead and tackle a practice problem to better understand this. This example problem says that a Japanese car is advertised as having a gas mileage of 15 kilometers per liter. Convert this rating to miles per gallon. So we're given 15 kilometers per liter, and we want our final answer in units of miles per gallon. So we're going to have two conversions here. We want to convert kilometers to miles and liters to gallons. So let's go ahead and sketch out how we're going to carry out this conversion. Now, we're starting off with kilometers. The first thing we can do is convert that to just meters, right? We know 1 kilometer is equal to 1,000 meters, and this is just because we know our metric prefixes. Then we can convert meters to yards. This is one of those conversion factors that I would recommend you be familiar with. 1 meter is equal to 1.094 yards. And then finally, we can convert yards to miles because we know 1 mile is equal to 1760 yards. Okay, so applying those conversion factors, we can go from kilometer to miles. What about converting liters to gallons? What's our workflow for that? Well, the first thing we can do is we can convert liters to quarts. 1 liter is equal to 1.06 quarts. And then we can take that and convert it to gallons because we know 4 quarts is equal to 1 gallon. So that's our workflow. Let's convert kilometers to miles first, and then we'll apply the conversion factors to go from liters to gallons. So to write this out, we'll start with that kilometers. We said our first conversion is from kilometers to meters, and we know that 1 kilometer is equal to 1,000 meters. Notice that we can go ahead and cancel out kilometers now. Then our second conversion is to go from meters to yards. 1 meter is equal to 1.094 yards. And now we can cancel out meters. Our last conversion factor then is to go from yards to miles, and we know that 1 mile is equal to 1760 yards. And notice how we're applying these conversions in a manner where we can cancel out units. So notice we put yards in the denominator here because right here, yards is in the numerator, and that way yards cancel out. And we saw the same thing with meters and kilometers. So there we go. These are the conversions we need to apply to convert from kilometers to miles. Now, we still need to do another kind of conversion. We need to go from liters to gallons. So now that we've gotten from kilometers to miles, let's apply some of the conversions we need to go from liters to gallons. Our first conversion is to go from 1 liter to quarts, which is 1.06 quarts. And then our last and final conversion is to convert from quarts to gallons. 4 quarts is equal to 1 gallon. And notice how liters cancel out, quarts cancels out, and we're left with gallons. The only units we have left is miles in the numerator and gallon in the denominator. And that is exactly what we wanted. If we go ahead and plug this into a calculator, plug in your numerator first, in parentheses, then divide by all the numbers in your denominator in parentheses. And what you're going to get as a final answer is 35.3 miles per gallon. So 15 kilometers per liter is equal to 35.3 miles per gallon. So that's how we can use dimensional analysis to convert from one system of units to another. Now we can go ahead and move into our second objective where we're going to discuss vectors and scalars. Kinematics is the study of motion without consideration of the forces that cause said motion. It provides a language and a mathematical framework for describing the position, velocity, and acceleration of objects. And central to kinematics is the distinction between vector and scalar quantities, which are both vital for describing different aspects of motion. Vector quantities have both magnitude and direction, making them essential for a complete description of certain physical phenomena. For instance, displacement is not merely how far an object has traveled, it's also the direction from its starting point to its final position. Velocity extends this concept to include how quickly an object changes its position, incorporating both speed and the direction of movement. Similarly, acceleration provides insight into how quickly an object changes its velocity, which is crucial for understanding dynamic systems. Other vector quantities like force and weight, they describe interactions and influences that have both strength and a specific direction of action. Take gravity, for example, which consistently pulls objects towards the Earth's center. Now, scalar quantities, by contrast, they describe magnitude without a directional component. Distance, for example, tells us how much ground an object has covered, but it doesn't specify a path or direction. Speed gives us the rate of distance covered per unit of time, but unlike velocity, it does not indicate where the object is heading. Mass, energy, density, and temperature, these are all scalar quantities as well. They provide a quantity or intensity level without indicating a particular direction. Now, I really want to focus on vectors, and I want to make note that vectors may be represented by arrows, and the direction of the arrow indicates the direction of the vector. The length of the arrow is proportional, usually proportional to the magnitude of the vector quantity. Now, common notations for a vector quantity are either an arrow or boldface. So for example, you might see a vector quantity represented as having an arrow on top of that vector, or you might see boldface. So it might be just a thicker letter to indicate a vector quantity. We're going to see a lot of this in our lectures for this playlist, but please keep in note that both of these notations are common and interchangeable. Now, the first thing we want to focus on and discuss is vector addition. Vector addition is the process of combining two or more vectors to obtain a resultant vector. This resultant vector represents the cumulative effect of the individual vectors. And there are two primary methods to add vectors. You can have graphical method or an analytical component method. The graphical method involves drawing vectors to scale and then using geometric principles to find the resultant vector. One common technique within the graphical method is the tip-to-tail method. The tip-to-tail method involves placing the tail of the second vector at the tip of the first vector. The resultant vector is then drawn from the tail of the first vector to the tip of the second vector. So the steps for carrying out this method is really simple. First, you want to draw out the first vector. Let's call it vector A. You're going to draw it on a coordinate plane or a piece of paper, maintaining the correct scale and direction. The second step is then to place the tail of the second vector, let's call it vector B, at the tip of vector A. Ensure that vector B is also drawn to scale and in the correct direction. Then the final step is to just draw the resultant vector, and the resultant vector is drawn from the tail of vector A to the tip of vector B. This vector represents the sum of vectors A and B, and it's helpful to label this vector as R. So that is the tip-to-tail method. What about the analytical method we were discussing earlier? Well, the analytical method involves breaking down vectors into their components along the coordinate axis, usually x and y axis, and then adding these components separately. And this method is particularly useful for precise calculations. So keeping this in mind, given any vector, let's say vector v, we can find the x and y components by drawing a right triangle with v as the hypotenuse. Then if theta is the angle between v and say the x component, then we can write that cosine theta is equal to x over v. And similarly, we can write that sine theta is going to be equal to y over v. We can rearrange these expressions to solve for x and y respectively. So x is equal to v cosine theta and y is equal to v sine theta. Now, on the other hand, if you know x and y, we can find v. V is going to be equal to the square root of x squared plus y squared. In addition to that, we can also find the angle for the resultant vector. This is going to be equal to the inverse tangent of y over x. So we have a lot of important equations here for this section for the analytical method, where we break down vectors into their components along the coordinate axis. So just to repeat, if you have vector v, you can solve for the x and y component of vector v using these two equations where x is equal to v cosine theta and y is equal to v sine theta. In addition, if you know x and y and you are trying to figure out v, v is equal to the square root of x squared plus y squared. And we can also calculate theta if we know information on x and y. Theta is equal to the inverse tangent of y over x. These are all extremely important equations to keep in mind because we're going to be dealing with vectors a lot in this curriculum. Now, let's go ahead and jump into a couple of example problems. This first example says, find the x and y components of the following vector v. V is equal to 10 meters per second, and theta is equal to 30 degrees. Now, to figure out the x component, this is just going to be v cosine theta. And we know v and we know theta, so it's just a matter of plugging those values in. 10 cosine 30 degrees. Now, if you do not know your values for cosine 30, and you're going to see sine 30 here as well, that is totally okay. We're going to cover these kinds of topics in chapter 10, where we discuss mathematics and how to approach mathematics on the MCAT. So don't freak out now. We're going to cover it later down the line. But what we have here is 10 cosine 30. This is going to be equal to 10 multiplied by cosine 30, which is equal to square root of 3 over 2. So this is going to be 10 square root of 3 over 2. And we can do some simplification here by dividing the numerator and denominator by 2, which gets us 5 square root of 3 meters per second. This is our x component for our vector v. What about for our y component? Our y component is going to be v sine theta, and that's going to be equal to 10 sine 30 degrees. Now, sine 30 degrees is equal to 1/2, so what we have here is 10 multiplied by 1/2, which is equal to 5 meters per second. So our y component for vector v is equal to 5 meters per second. And we've answered this example problem. What about this next one? This next example says, what is the magnitude of the vector with the following components? X is equal to 3 meters per second, and y is equal to 4 meters per second. Now, to calculate the magnitude of our vector v, this is just going to be the square root of x squared plus y squared. And we're given the value for x and y, so we're just going to go ahead and plug it in. It's going to be the square root of 3 squared plus 4 squared. Now, 3 squared is equal to 9, that's 3 times 3, and 4 squared is equal to 4 times 4, which is 16. So what we have inside this square root is 9 plus 16, which is equal to 25. Now the square root of 25 is equal to 5, and the magnitude of our vector is 5 meters per second. Now that we understand how to do this, the next thing I want to talk about is what happens when we're adding multiple vectors? So when we're adding multiple vectors, the analytical method allows us to sum the individual x and y components separately. So let's say our goal is to add vector 1 plus vector 2 plus vector 3. v1 plus v2 plus v3 gives us our final resultant vector r. How are we going to do this if we are given the x and y component for each of these vectors? Well, when we're adding multiple vectors, the analytical method approach ensures that our final resultant vector is going to account for the contributions, all of the contributions along each axis. So what that means is that the x component of our resultant vector is simply the sum of the x component of the vectors being added. It's simply going to be x1 plus x2 plus x3, and that gives us our new x component for our resultant vector. Similarly, the y component of a resultant vector is simply the sum of the y components of the vectors being added. So it's going to be y1 plus y2 plus y3, and that gives us our y component for the resultant vector. Now that we have the x and y components of our resultant vector, we can go ahead and figure out the magnitude of the resultant by using the Pythagorean theorem. So r is going to be equal to the square root of x squared plus y squared. All right, keeping in mind that x and y for this resultant vector is the sum of the x components for this x variable, and this y is the sum of all the y components of the three vectors that we have summed together. Similarly, we can figure out theta for this resultant by using the relationship theta is equal to inverse tangent of y over x. Wonderful. So now that we understand how to add multiple vectors, let's go ahead and start to talk about vector subtraction. Vector subtraction is closely related to vector addition, and the principles that we've established for addition can be directly applied with a few modifications. Now, vector subtraction, it can be thought of as adding the opposite or negative of a vector. Specifically, subtracting one vector from another is equivalent to adding the first vector to the negative of the second vector. And this can be expressed mathematically. We can say that vector A minus vector B is the same as saying vector A plus the negative of vector B. So as with vector addition, here, the x component of the resultant vector is going to be the difference of the x components of the vectors being subtracted. And similarly, the y component of the resultant vector is just the difference of the y components of the vectors being subtracted. And you'll notice that when you subtract vectors, you are simply flipping the direction of the vector being subtracted and then following the same rules as normal. Now, what about multiplying vectors by scalars? When we multiply a vector by a scalar, the result is a new vector. This operation affects the magnitude of the vector, but the direction of the vector might or might not change. That depends on the scalar. So let's talk about it. The magnitude of the resulting vector is going to change based on the scalar value that you're multiplying the vector by. If the scalar value is greater than 1, then the magnitude of the new vector is going to be greater. Let me repeat that. If the scalar is greater than 1, then the magnitude of the vector is going to increase. If the scalar is between 0 and 1, then the magnitude will decrease. If the scalar is negative, the magnitude will still change, but the direction of the vector will also reverse. And so for our direction, we can simplify this by saying that if the scalar n is positive, the new vector b will point in the same direction as the original vector a. If the scalar n is negative, then the new vector b is going to point in the opposite direction of the original vector a. So mathematically, we can express this multiplication of vectors by scalars as b equals na. And again, if n is positive, vectors b and a will point in the same direction. And if n, the scalar, is negative, then the vectors b and a will point in the opposite direction. Now, this operation is really straightforward, but it's really powerful because it allows us to scale vectors up or down and even reverse their direction depending on the scalar used, depending on the scalar that we're going to multiply the vector by. So that is multiplying vectors by scalars. Now, the last thing we want to discuss in regards to vectors is what happens when we multiply vectors by other vectors. When multiplying vectors by other vectors, we have two key operations, the dot product and the cross product. Each of these operations serves a different purpose and it produces different types of results. Let's start by discussing the dot product. The dot product is a mathematical operation between two vectors that produces a scalar as the result. It produces a single number as the result. This operation essentially measures how much two vectors overlap in the same direction. And the formula for the dot product of two vectors is equal to the magnitude, all right, the absolute value of vector A multiplied by the absolute value of vector B multiplied by cosine theta, where theta is the angle between the two vectors. Now, the dot product is really useful in calculating things like work done by a force on an object, as well as calculating projections and angles between vectors. We're going to see this in a future chapter where we will discuss work in depth. Now, the result for a dot product is largest when the vectors are aligned. So it'll be the largest when theta is equal to 0 degrees, meaning that the vectors point in the same direction. And the dot product is going to equal 0 when the vectors are perpendicular to each other. So when theta is equal to 90 degrees. What about the cross product? The cross product is another mathematical operation between two vectors. But unlike the dot product, it produces a vector as the result. The resulting vector is going to be perpendicular to the plane formed by the original two vectors. The formula for the cross product of two vectors is equal to the magnitudes of the vectors, so the absolute value of vector A and B multiplied together, and that's going to be multiplied by sine theta, where theta is the angle between the two vectors. Now, we're multiplying these two vectors together and it produces a vector as the result. If we're producing a vector as a result, keep in mind vectors have magnitude and direction. How do we figure out the direction of our produced vector, our vector from the cross product? Well, the direction of the resultant vector is determined using the right-hand rule. So to do this, you're going to point your thumb in the direction of the first vector A. You're going to extend your fingers in the direction of the second vector B, all right? And then your palm will face the direction of the resultant vector C. You can also, instead of using your palm, use your middle finger to point in the direction for vector C. All right, so that is how we figure out the direction of the resultant vector using the right-hand rule. The cross product, it's very useful in physics. It's really useful in calculating torque, angular momentum, and magnetic fields. And we're going to see all of these topics in later chapters, and we'll use our right-hand rule again. The cross product also is going to be 0 when the two vectors are parallel. So when theta is equal to 0 degrees or 180 degrees, then the cross product is 0. All right? This makes sense because the sine of 0 degrees and the sine of 180 degrees is 0. Okay, and again, this makes sense because no area is formed if the vectors are in the same or opposite directions. So again, the cross product is 0 when the two vectors are parallel. Keeping this information in mind for the dot product and the cross product, let's go ahead and tackle a practice problem. This problem asks, what are the magnitudes and directions of the resultant vectors from the following cross products? So we're trying to figure out vector C, which is the cross product of A and B, and vector D, which is the cross product of vector B and A. And we're given information about the X and Y components for vectors A and B. So let's go ahead and do this first cross product. C is equal to A cross B. The first thing that we want to do is go ahead and draw our vectors on a graph. So here's our x-axis, here's our y-axis. And A, we're told, has an x component of -3 and a y component of 0. So vector A looks something like this. As for vector B, we're told that it has an x component of 0 and a y component of +4. So vector B looks something like this. So this is vector B, this is vector A, and what you notice is that the angle between them is 90 degrees. This is a right angle right here. So we just figured out theta, which is extremely important and required for us to carry out this cross product. So theta is 90 degrees. Now, the cross product of A and B is going to be equal to the magnitudes of A and B multiplied together by sine theta. Let's go ahead and figure out the magnitudes of vector A and B. We're going to use our equation. Vector A is equal to the square root of x squared plus y squared. So this is going to be equal to -3 squared plus 0 squared. That's going to give us 9 plus 0, which is 9. And the square root of 9 is equal to 3. So A is equal to 3 newtons. What about vector B? What's the magnitude of vector B? We're going to do the same thing. It's going to be the square root of x squared plus y squared, which is 0 squared plus 4 squared. That's going to give us the square root of 16, which is equal to 4. So vector B is 4 meters. And this is going to be multiplied by sine theta. Theta is 90 degrees. Now sine theta, sine 90 degrees, this is equal to 1. So what we have here is 3 times 4 times 1, which is equal to 12 newtons multiplied by meters. Okay, so that's the magnitude of vector C. What about the direction for vector C? Now to do this, we got to use our right-hand rule. So let's look at this graph, all right? Hopefully you're using your iPad just like I am right now filming this video. And we're going to stare at our screen. We're going to point our thumb in the direction of vector A. So our thumb should point to the left. Then the rest of your fingers should point in the direction of vector B, so up. All right, and notice how with your thumb to the left and the rest of your fingers up, there's 90-degree angle between your thumb and your other fingers. Now, where is your palm pointing? Your palm is pointing downwards. So the direction of vector C is into the page. We could also draw that out on our graph and it would be in our z-axis. So vector C has a magnitude of 12 newtons times meter, and its direction is into the page. Okay, that's the first part. Now the second part, we want to calculate the magnitude and direction of vector D, which is B cross A. Now what you notice here is that the magnitude should be the same because this is going to equal the magnitude of B multiplied by the magnitude of A sine theta. And B is 4 meters. That's the magnitude of vector B. We just figured that out. And for A, it is 3 newtons. And sine theta, sine 90 degrees is just 1. So we have the same magnitude for vector D. The difference here is going to be the direction. Now what we want to do is point our thumb in the direction of vector B. So our thumb is going to point upwards. And then the rest of our fingers are going to point in the direction of vector A to the left. And what you notice now is that your palm is facing upwards, out of the page. All right? And so the direction for vector D is out of the page. They have the same magnitude. The direction differs based off of the vector order that you're carrying out your cross product. So A cross B is different than B cross A, not in magnitude, but in direction. And that's how we're going to solve this problem. Now, that's everything that I'm going to cover in this first video for chapter 1. In the next video, we'll pick back up on objective 3, where we're going to discuss displacement and velocity. I hope this video has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.